Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera to Dr. Coil and Dr. Siti Emily. My name is Faris bin Nordin. So today I will be presenting about my final project with title Winding Slot Improvement Analysis of Radial Field Excitation, Coil Flux Switching Motor for Optimal Performance. So for part introduction, in 1950, FSM, which is flux switching motor, was introduced in electric motor. FSM divided by three parts, which is permanent magnet flux switching motor, field excitation flux switching motor, and the last one in hybrid excitation flux switching motor. In HEFSM, we combine with permanent magnet and FEC on the stator to produce flux. So for this design, HEFSM is designed in radial FEC. So basically, the function of FEC is to give more strength on the flux. HEFSM for the operation is to exchanging the polarity of the FEC flux link with the armature coil to the rotor position. So advantage for the HEFSM is will give more maximum torque, power and more efficiency motor. Next is problem statement. There is an overlap winding problem between armature and radial FEC winding. So this figure show the problem. This armature, this is for the FEC in radial condition. So basically, armature and FEC have their own polarity, which is positive and negative. So this figure I already sketched the polarity. This polarity for the armature, this polarity for the FEC. We know that the flux line will go from negative to positive. We can see this arrow for the flux line for the armature, this flux line for the FEC. What the problem here is overlap happen when the armature negative polarity attract with the FEC in radial condition positive polarity here. So this what we call it overlap winding. Okay, the effect from the overlap winding is cause the height coil end to have height losses and high flux saturation in flux distribution, and also will decrease the efficiency. Okay, to prevent the overlap winding FEC, FEC slot and armature coil slot used to be improved. Next is for part objective. The first objective is to improve the flux distribution of armature and field excitation winding slot of HEFSM. Second is to examine the optimal of motor performance in terms of cogging torque, back EMF, flux leakage, flux distribution, and output torque of HEFSM. So for the scope, the first scope is the specification and limit for the silent rotor is 12 slot and 14 pole HEFSM is purpose for this project. So basically, table 1 show the specification of the HEFSM that we will design. So the diameter of the stator is 134.5 millimeter and the radius of the rotor is 97.25 millimeter. So the angle for rotor is 12.8571. The stator angle is 15. So we use the permanent magnet weight is 1 kilogram. Next scope is the analysis of performance divided by 2, which is no load and load. For no load, we will analyze in terms of cogging torque, back EMF, flux leakage, flux distribution. And for no load, we will analyze in terms of torque JE at various JA to be analyzed by using JMAT Designer. For the restriction for electric of maximum 650 volt for bus voltage and maximum current is we use 360. For the armature current density JA and FEC current density, we use fixed at 30 ampere milli area. So next part is methodology part. This is for the flowchart how to design the HEFSM design. First, in geometry, we need to sketch the rotor, stator, permanent magnet, slot FEC, and armature coil. If the design have overlap design, we need to change the parameter or check. If the design no overlap, we go to the JMAT Designer to set the materials, condition, circuit, mesh, and study. If not success in part setting materials, we need to revise back and change the setting. If success, we go to the coil analysis, zero rotor position. In zero rotor position, we need to adjust the initial angle for the rotor. So from the coil test, we will choose the angle U phase in between range 90 and 270. If no, we need to back to the coil test and change the angle of rotor. So if yes, we go to the three-phase arrangement. So this figure shows the complete design of the HCFSM for 12 slot and 4 poles HCFSM. So this is flowchart for the coil test analysis. First of all, we need to analyze 12 coil tests. So this is for the example how I generate the 12 coil tests. In 12 coil tests, we will divide by 3 group coil tests, which is U, V, W. This procedure how to set up the three-phase system. To determine U phase, for the principle in U phase is the angle must be 90 to 270 degree in waveform. So we choose this waveform as U because the angle in range 90 and 270 degree. So we choose this for the U, V, W. So after choose U, V, W, we will set up to the circuit at JMac designer to make a three-phase system. So this is for the result for the 12 coil test analysis. So basically in 12 coil test analysis, the current we set to 0. So only permanent magnet as a primary source will generate magnetic flux. And in this 12 coil test also we'll set the negative 2.2 degree for the initial rotor position to set the 90 until 270 as a U phase. So basically this 3 graph is from the 12 coil test. This group for U, this group for V, this group for W. So in group U we have coil 3, coil 6, coil 9 and coil 12. In group V we have coil 1, coil 4, coil 7 and coil 10. For the coil W we have coil 2, coil 5, coil 8 and coil 11. Basically from the 12 coil test we combine one graph to the 4 coil. This is for the coil test analysis. First is convert single phase to 3 phase. So basically 12 coil test analysis is a single phase. Then 3 coil test analysis is convert from single phase to 3 phase. So which is waveform UVW we will combine in one graph. So this is for the graph UVW phase. So the maximum amplitude of the magnetic flux is 0.03183. Next we move to the no load test analysis. Cogging torque need to be analyzed in this project. The cogging torque will happen when there is an air gap in the machine, means like in the machine we have air gap between rotor and stator. So when the cogging torque high will cause the effect to the machine, means like vibration and noise. So the vibration is not good for the machine. So in conventional design I get the cogging torque is 9.6 Newton torque peak to peak. For the back EMF, back EMF is happen when the voltage generated in electric motor when there is in lattice motion between the stator winding and the rotor magnetic field. So the maximum value for the induced voltage or back EMF for the conventional design is 54.921 volt. So the induced voltage waveform is less distortion, can be provide good practical application. So based on this waveform is most likely same to sinusoidal graph. So we can see here less distortion, but for the improving, we will improve for the better sinusoidal graph for back EMF. Next, we move to the floodline for no load test analysis. So in no load test, we set the current to 0. So basically, permanent magnet will generate or produce the flux. So basically, most of the flux will flow to the stator around the FEC. So flux will go to the rotor, which is high flux flow into the rotor cause the high air gap density. This will be cause of the flux cancellation, since when the air gap is very high, means like value is air gap is very big, will give more flux cancellation happen. So we move to the flux distribution. So the maximum and minimum flux distribution is for maximum 1.8932 T-torque, and for minimum 0.000172 T-torque respectively, based on this value. So we can see here very much flux saturation at the FEC. So flux saturation will affect on the performance of the motor, and also we will give the flux cancellation also to the motor. So the last part for the result is load test analysis, which is torque performance of FEC density JE at various armature current density JA. So this is for the graph of the average output torque versus JE at various JA. So basically this step will referring to this graph. So when JE and JA equal to 0, JE and JA equal to 0, the torque result obtained approximately equal to 0, and constantly until 30 JE. We can see here because no current injected into JE and JA, only depending on the permanent magnet to generate the flux. So we move to the point number 2, which is JA is set between 5 to 20, which is 5, JA 5 until this blue JA 20. The output torque maintain constant. The output torque maintain constant at 25 JE. We can see here output torque maintain after 25 JE. So for the point number 3 is JA at 25 and JA at 30. So you can see JA at 25 and JA at 30. The maximum output torque obtained for the 25 JA 25 is 278.889 Newton torque. For the 30 for the JA 30 we produce the torque at 295.26 Newton torque respectively. So the JE for the 30, where much FEC flux is generated and the torque is increased, it shows that there is no any magnetic saturation or flux cancellation. So in conclusion for this project is the no load and load test for the output performance has been analyzed. The average output torque versus JE at various JE is approximately 295.26 Newton torque. The jogging torque for this project is 9.6 Newton torque, and the back EMF is 54.921 volt. So the details need to be investigated for the amateur, and FEC coil has the potential to improve the performance. So basically in this conclusion we just finish for the conventional design for the FIP2. We will improve from the conventional design to be better performance. So for the recommendation, the amateur and FEC coil slot need to be improved to get the better performance or optimal performance by follow the no load and load test analysis for the 12 slot and 4 poles HEFSM. So that's all for me. Thank you.